Welcome back again. Here we will discuss about the moving coil and moving iron type instruments. So electrical measuring instruments, they are classified into two types. One is moving coil instrument, another one is a moving iron instrument. Moving coil instruments, they are classified into two. One is permanent magnet type, another one is a dynamometer type. And moving iron type instruments, they are also classified into two types, attraction type and repulsion type. So first we will see the moving coil type instrument, PMMC type moving coil instrument. PMMC is permanent magnet moving coil, which is a type of the measuring instrument. It will allow to measure the current flowing through the coil or conductor by observing the coil angular deflection in uniform magnetic field. Now, in order to create the stationary magnetic field in PMMC type instrument, we use the permanent magnets. In between the coil moves. So let us see the construction working principle of this PMMC type moving coil instrument. So this moving coil, here it is shown as a brown color. This is a moving coil. This moving coil, it is wound on a rectangular aluminium former. Okay, it is shown here by this rectangular white color shape, okay, which is called the former. So on this rectangular former, the moving coil is wound, okay, and this moving coil, it is placed between the permanent magnet. So this permanent magnet, it is generating the constant field. Here if we have the north pole, here we will be having the south pole. Okay, this permanent magnet, it is made up of alcomax and alnico material. On this pointer, on this moving coil, with this moving coil we have this spindle attached. At the two end of the spindle we have the jewel bearing. With this moving coil also the pointer is attached, and through this pointer the spring is also attached. This spring is made up of the phosphorus bronze material. So if there is any deflection in the pointer, we can observe it on the scale. Now whenever the electric current flows through this moving coil, then since this moving coil is placed in a stationary magnetic field, so what will happen? This moving coil, it is placed in a stationary magnetic field, right? So as a result, a torque will act on this moving coil, and this moving coil will experience a force. The direction of the force acting on this moving coil can be found from the Fleming's left hand rule. Okay, what it says, if this index finger, middle finger and this thumb, if they are placed perpendicular to each other, if the index finger represents the direction of the magnetic field, if the middle finger represents the direction of the current, then thumb will represent the direction of the force. So using this Fleming's left hand rule, we can measure the direction of the force. Now as this coil moves, with this coil this pointer is attached, so this pointer will also move, and the deflection of the pointer we can observe in the scale, and this deflection of the pointer is happening due to the deflecting torque. Now here the spring attached to this spindle will provide the controlling torque for the pointer, which will bring back this pointer from its full scale position to the initial value, and here the eddy current will provide the damping torque to have the steady state deflection of the pointer on the scale. Okay. Next, we will discuss about the applied force on the conductor, which is F equals to NBIL. Unit is Newton. So deflecting torque, what is the expression of deflecting torque in PMMC? It is expressed as Td equals to force into displacement, or Td equals to NBIL into D. So this L and D we can write together, this length and this D displacement, it can be written as A, which is the cross-sectional area of the coil. So from this relation we can see that the deflecting torque is directly proportional to the current. And here spring is providing the controlling torque. When the spring is getting twisted, the controlling torque, it is directly proportional to the angular deflection phi. So Tc equals to Kc into phi. Kc is the spring constant. So at steady state, this deflecting torque and controlling torque, they are equal. So if we equate the expressions of deflecting torque and controlling torque, we will get NBAI equals to Kc into phi. That means here the current is directly proportional to the angular displacement phi. Since it is directly proportional, so the PMMC has uniform scale. Next, we will discuss about the dynamometer type moving coil instrument. It is a modified version of the PMMC instrument that is used for measuring the voltage and current. And this instrument consists of electromagnets, so it is also called as the electrodynamometer type instrument. This dynamometer type instrument can be used AC as well as DC circuit. It can also be used as ammeter, voltmeter and wattmeter. So let us see the construction and working principle of the dynamometer type moving coil instrument. So here what we have the fixed coil. The fixed coil is splitted into the two equal parts. These two are my fixed coil. In between we have the moving coil. This moving coil is wound on a non-metallic former. With this moving coil, a resistor is connected in series to limit the input supply current. With this moving coil, the pointer is attached. Now when we are giving the supply to this fixed coil, a magnetic field will get generated in the fixed coil, and the same supply will also go to the moving coil. So what will happen? The same supply goes to the moving coil. This moving coil, it is getting the same supply which is placed between the magnetized fixed coil. So moving coil will experience a force, and the direction of the force can be found from the Fleming's left-hand rule. Now when the moving coil starts moving, the pointer attached to it will also be deflected from its initial position to the full scale value due to the deflecting torque. And here the air friction damping will provide the required damping torque to have the steady state deflection of the pointer on the scale. And we can use the spring control technique to provide the controlling torque. Next, we will see the expression for deflecting torque in this dynamometer type moving coil instrument. It is given by I1 I2 multiplied by dm d phi, where I1 is the current flowing in the fixed coil, I2 is the current flowing in the moving coil, and phi is the angular deflection, where dm d phi is a change in the mutual inductance between the fixed and the moving coil with respect to the deflection in radian. Now, dynamometer with DC, the deflecting torque will be I1 I2 into dm d phi, controlling torque is K phi. We know at steady state Td equals to Tc. So just equate these two expressions, we will get phi equals to I1 I2 by K into dm d phi. Next, if it is an AC type dynamometer, so in that case, the expression of I1 will be Im1 sine omega t and I2 will be Im2 sine omega t minus 5. So what will be the RMS value of this I1? Im1 by root 2, and for this RMS value will be Im2 by root 2. So in this case, the deflecting torque Td will be I1 I2 cos phi into dmd phi, and controlling torque Tc equals to k phi. And final steady state position Td equals to Tc. We can equate these two expressions to get a relationship between phi and I1 I2. Next, when the dynamometer it is used as an ammeter, then phi is directly proportional to I square, and when it is used as a voltmeter, phi is directly proportional to V square. So from here we can conclude that the scale of the dynamometer type instrument, it is not uniform unlike the PMMC. Next is repulsion type moving iron instrument. Here we have this moving iron plate and this fixed iron plate, and there is a cylindrical coil attached to the fixed iron plate. Okay. Now if we give the electric supply in the cylindrical coil, this cylindrical coil will get magnetized, it will generate a magnetic field, and it will act as an electromagnet. And here inside, with the moving iron plate, a shaft is attached, and with this shaft a spring and the pointer is attached. The deflection of the pointer can be measured in the calibrated scale. So when this magnetic field is getting induced in the cylindrical coil, it will also magnetize this moving and the fixed iron plate with the same polarity. Means if the north pole is created in the moving iron plate, same north pole will also be created in the fixed iron plate. As a result, this moving and the fixed iron plates, they will repel each other. A repulsion force will be acting between these two, and this moving coil will start getting repelled away from the fixed coil. As a result, the pointer attached to it will be deflected due to the deflecting torque, which we can observe in the scale, and here the controlling torque will provide the required torque, controlling torque. This spring attached to this shaft, it will provide the required controlling torque. Now, suppose I want to measure unknown current using the repulsion type moving iron instrument. Here, whatever the current I am supplying, let's say I don't know the value. So that amount of the magnetic field will be directly proportional to the current that you are applying here. Okay. Now, what will happen? It will magnetize these fixed and moving iron coils also. Now, accordingly, a repulsion force will be acting between them. Moving iron plate will be moving away, and this pointer will get deflected. The reading, in this case, the pointer will be showing on the scale, that will be the value of the current or voltage that you are supplying over here. Okay. Next is attraction type moving iron instrument. In this instrument, at the top and the bottom side, we have the fixed coil, and at the right corner of the instrument we have a shaft attached. With that, a soft iron, a shaft or spindle is attached. With that, a soft iron disc and the pointer is attached. Okay. Now, at one point of this spindle we have this air damping chamber. In this air damping chamber we have the aluminium piston. So this piston will be having the friction with the air to supply the damping torque. Now whenever electric current flows in this fixed coil, it will generate the magnetic field. As a result, this soft iron core will get attracted towards the magnetic field, and the pointer will get deflected due to the deflecting torque. Okay. Now higher the electric current in this fixed coil, higher will be the magnetic field, higher will be the force of attraction between this magnetic field and this soft iron disc. Okay. Next, this attraction type instrument, we are using this moving iron disc for measuring the current and voltage. And here we are using the electromagnet that will operate on the principle of the magnetic attraction. So these type of instruments can be used as voltmeter, ammeter or wattmeter. Now the deflecting torque in this instrument will be depending upon the force applied on the iron disc, where F is directly proportional to mH. What is F? Applied force. M is the force strength of iron piece. H is the field produced by the coil. So if M is directly proportional to H, from this relation we can write F is directly proportional to H square and H is directly proportional to I. That means higher the electric current, higher will be the magnetic field and higher will be the force of attraction. So if H is directly proportional to I, from this relation we can write F is directly proportional to I square. That means the deflecting torque, it is force into displacement. So deflecting torque, it is directly proportional to I square. Since deflecting torque, it is directly proportional to force. And what about the controlling torque? TC, it is directly proportional to phi. So at steady state, deflecting torque we know which is equal to the controlling torque.